So the fact is that even if there is more, the weight of the lead is larger here, and the weight of the lead is made by the mass of the lead times g, and here's the mass of the lead times a. So even though the resultant is bigger in the case of the lead, it also has to move a larger mass. It's got to accelerate a larger mass, and therefore the acceleration is going to be smaller, and it completely cancels out. You can divide both sides by ml, and then you're just left by g is equal to a. So if there's no air resistance, the weight of lead will accelerate at g meters per second, which is 9.8, or you use in GCSE 10 meters per second squared. This would be the acceleration. And here it's the same thing. The mass of the plastic cancels, and it just the acceleration will be equal to g, which is again 10 meters per second squared. Okay, so hopefully that makes sense, and you see that if there's no air resistance, everything accelerates at the same speed, because even if there's more resultant force, it needs to move a larger mass, and gravity behaves in such a way that those two things cancel exactly, and so you end up with the same acceleration for everything. That's why in the moon a feather and a rock will both fall at the same time. You drop them both, if there's no atmosphere there, they both fall at the same time, because the weight doesn't matter. Okay, so hopefully that makes sense. Now let's have a look at question 23. Run out of space here. Let's go over there. Question 23 says, what are the two different parts of the overall stopping distance of a car? So this one's pretty logical. The first part of the stopping distance is the reaction time. So the time that you take from where you see the fact that you have to stop, reaction time, the reaction distance. Actually, normally you call it, even though the reaction time is basically what it's made up of, you call it in GCSE, normally we get asked to write it in terms of the thinking distance. Pressed the wrong button. Thinking distance. That would be that much, and or just some much, and some amount, and then there would be the second part, which would be the actual braking distance. Sorry, braking distance. So one of them is the time you take between when you see the thing and you start braking, and the other one is the time that the car actually takes to brake. So the stopping distance is the name we normally doing in a different color. The stopping distance is made up of the thinking distance plus the plus the braking distance. So that's pretty straightforward. We can go on to the next question. Oh, the other thing to mention is obviously the faster you're going, the faster this is. The longer that is, and the longer that is. They're both really long. The faster you're going, the more time you'll travel in the same thinking time, the more distance you'll travel in the same thinking time, and the longer it will take the car to brake. So that you'd be surprised by how much this increases with just increasing your velocity by a small amount. So especially if you're going around the motorbikes, you've got to take all of this really into account, because in a motorbike it's very hard to change your direction, because you've got to drop yourself to one side before you can turn. So you've got the time, not only you've got the thinking and the braking, you also, if you've got to change direction, you need to take time to actually drop. Your motorbike's like this, you're there on top driving away, you've got to allow yourself to drop to one side so that you can then turn. It's an exaggeration, but first you drop and then you can turn, and the time it takes to do that you also have to take into account. So yeah, be careful basically if you're going on a motorbike, please. It's important. Okay, so 24. said list 3 or 4 factors which affect the 2 sections of stopping distance. 3 or 4 factors which affect the 2 sections of stopping distance. So let's see, thinking distance, factors that affect the thinking distance. I already mentioned one of them. It's 1. So how fast you're going. How fast you're going. 2, the visibility, so like literally how much you can see. So something might happen and you're not able to distinguish it very well, so while you're looking at it you're still trying to figure it out what it is and whether you have to stop or not. So your thinking distance could be increased. And also how awake you are, how you're feeling, how awake you are. If you obviously, people who drink a few beers and then go in the car and they're feeling drowsy, or they've been driving for 4 hours or whatever, how awake or alert you are. Alright, so those are all pretty common sense. Then these are all for thinking distance, right? Thinking distance, which we had in white. Thinking distance. And now for the other one, for the braking distance, we have also how fast. That will also affect the braking distance, obviously, how fast you're going. And the second one would be, for example, how much weight, how much mass you're carrying in your car. So how heavy is your vehicle, or how much are you carrying, right? Because this won't affect the thinking distance, but it'll definitely affect the braking distance. Also the condition of the road, if it's wet or if it's icy or whatever of the road, and the condition of of your brakes and your tires. So a condition of brakes and tires. All of this will so this is the road and the weather, etc. Road and the weather. So the road could be a bad road also, just independently of the weather, or the weather could be bad. Alright, so all of these are factors that could influence both the thinking speed, the thinking distance, and the braking distance. And so all of these are for the braking distance. They influence the braking distance. Okay, it's an N. Alright, so let's go to the next question. If I can only find it. Okay, so question 25. Question 25 says, what's the formula for work? A crazy dog drags a big branch, some other stuff. So first I'll do the work done. So the formula for work done is what they're asking us for. And the formula for work done is the force that you're applying to something, force applied, or just force, you have to remember applied force, time multiplied by the distance moved. Okay, so in other words, if you were pushing on something but it wasn't moving at all, then according to the laws of what we call work done, then you wouldn't do any work, even if you're sweating and you're getting tired. If the thing is not moving, you're not doing any work, no useful work anyway. It's called like that, work done. And the units of work done are joules. joules. Okay, and in the second part of the in the question it says a crazy dog drags a big branch 12 meters over the next door neighbor's front lawn, pulling with a force of 535 newtons. So they tell you everything you need to know, and then you can say, okay, so the work done is going to equal the 535 newtons which the dog is putting into his work, times 12 meters of the branch. And on the calculator this comes out to be 535 times 12, 6,420 joules, and that's already to three significant figures, because these three are significant, and this one in this case it is, because it's telling us it's well, we'll go over a video of significant figures on some other point, but this is already the three significant figures, so we can leave it like that. Work done is 6,420 joules. So that's easy, the formula for work done. And in question 26 they ask different. They say, they ask an other important formula, which is kinetic energy. What's the formula for kinetic energy? So kinetic energy is just worked out by multiplying 0.5 or half times the mass of whatever's got the energy times the velocity squared. So that's normally written without the dots, and it's just half mv squared, but they mean times. And so if they ask us a question, which they're about to, they would have to give us the mass and the velocity of the thing to be able to calculate the kinetic energy. So here they go, and they say find the kinetic energy of a 78 kilo sheep moving at 23 meters per second. So we can go immediately and say, well, you've given me everything that I need for my formula, which is 1/2 times the mass, 78, times, be careful here with the square, okay, in the calculator, just the 23, which is the velocity, is the only thing that is squared, not the mass. Otherwise the formula would be like that, and that's not the formula. Formula is mv squared, so only the v is squared. Right, so here we square the 23 and not the 78, and if we put that in the calculator, I always do the squared part first, so I say 23 squared times 78 times 0.5 or divided by 2 is the same thing, and we get for the kinetic energy 20,631 joules, and this is not to three significant figures, so if we did want to put it to three significant figures, it would be 20, that's significant, that's after the first non-zero number, so that's also significant, and this is significant, so that's 6. This rounds down to 0 joules. So you can also write that as 20.6 kilojoules, where kilojoule is 1000 joules. That would be your three significant figures for the kinetic energy. And then the next question, we only have a couple of minutes left, but we'll do let me see. The next question was explain why the stopping distance of a car increases so much with speed. Why the stopping distance of a car increases so much with speed. Okay, it's not proportional if you increases so much with speed, and it's not proportional if you're going at 20 and then you're going at 40. The distance doesn't double, the distance is like 4 times as much. So why does that happen? Why is it not really proportional and more dramatic than that? Well, it's got to do with the things that we've just calculated, the kinetic energy of something and the work done of some by something. Basically, if a car's got a certain kinetic energy, a car has a certain amount of kinetic energy which is proportional to the velocity squared. It's not proportional to the velocity, it's the velocity squared. And the brakes of your car, independent of your thinking, which obviously that also the thinking time also, if it's the same, then the thinking distance when you're going at a faster speed is much bigger. But the brakes have to do work, okay, and that's an amount of force over an amount of distance in order to stop you, and the amount of work that they need to do to stop you is exactly the same as the kinetic energy that you have. Right? And so if your kinetic energy is proportional to your velocity squared, then the amount of work they have to do is also proportional to the velocity squared.